All right, the next part of this chapter is the mechanisms and the reactions that you can do with acid chlorides and anhydrides and esters and amides and nitriles and carboxylic acids. What can you do with these? How do you interconvert them? And basically, it's based on the same mechanism over and over and over and over again. Okay, this is basically what the mechanism is. You're going to have a carbonyl, and you're going to have one of 5 possible X groups, where X can either be a chlorine for the acid chloride, an OH for carboxylic acid, the anhydride is the O carbonyl, or ester is this group. What am I missing? Also a nitrile possibility. No, not nitrile. Nitrile won't be. Actually, I think it looks like it's only 4. Chlorine. Oh, an amide. Sorry, I forgot the amide. NR2. Okay. These are the 5 possible groups that X could be. Either chlorine, OH, the anhydride, the RO, and the NR2. Okay? So what you're going to do is add some sort of nucleophile to it. And what the nucleophile does is it substitutes for X. So your final product is R nuc plus X minus. That's what the reaction is. Very simple. It's a nucleophilic acyl substitution. You're using a nucleophile to substitute on the acyl group. I don't remember if we talked about this, but acyl is another name for a carbonyl. Actually, yeah, the Friedel-Crafts acylation that puts on a carbonyl on your aromatic ring. So we have talked about that. Okay, that's an acyl group. So you basically you're taking a nucleophile and substituting for whatever X is. And in this chapter, X is one of these 5 possibilities. Now, not all of these 5 are equally reactive. Some of them are slower, some of them are faster reactions. Okay? The chloride, the acid chloride, is the fastest and the best of all of the reactions. So if you want to do this reaction up here, the best thing to do is have the acid chloride, have X as the chloride, and add in whatever nucleophile. Next in reactivity is the anhydride. The anhydride is next in reactivity. Then you kind of have the ester and the carboxylic acid are almost equivalent. I'm going to put the carboxylic acid down here. And then finally the amide, again I don't have room here, but put in the amide, is the least reactive. And that's actually a good thing. Our bodies are made of amide bonds. Okay, all of our proteins, our skin, our muscle, everything is made out of amides. They're very, very non-reactive, and whereas an acid chlorides are very reactive. So, for example, you can take water and throw it on acid chloride, and it will immediately react. Very exothermic reaction. But if you take water and put it on amides, nothing happens. Like you take a shower, don't you? And your hair, nothing happens to your hair, nothing happens to your skin, nothing happens to your nails. All right, all you do is you just wash your body. Well, if your body was made of acid chloride and you went into the shower, you just completely dissolve and become a puddle. Amides don't react with water. So like I said, it's a good thing, otherwise you'd be a puddle. All right, so as far as reactivity, the acid chloride is the most reactive, then the anhydride, then the ester and carboxylic acid are equivalent. The carboxylic acid is a special case, which we'll talk about. Finally, the amides are the least of the reactivity of these groups. Okay, and basically what the mechanism is, let's go over the mechanism, a general mechanism. So you take one of these, let's just put X, and add a nucleophile. The mechanism is your nucleophile comes in here, adds to your carbon, kicks up your pi bond. We've talked about why this happens. All right, the carbonyl, the carbon is partial positive. You have you have a weak bond. You have the pi bond, so that's why it attacks there. And you form this O negative. What happens then is the lone pairs that you gain on this oxygen pop back down and kick out your leaving group. This intermediate is called the tetrahedral intermediate, because you're going from a trigonal planar intermediate to a tetrahedral intermediate. So that's why it's called, a trigonal planar reactant to a tetrahedral intermediate. And you form your product, then you kind of see how you get your nucleophile, plus X minus. Okay? And all depending on X, the reaction either goes really fast, it goes kind of fast, or basically it doesn't go at all. All right, so we're going to learn various reactions. based off of this list. Let me rewrite the list again. Okay, Cl. And basically what you can do, here's kind of a good way to look at it. It's kind of going to summarize this whole entire chapter in one thing. And the amide, we can never squeeze it in there. And we'll put a carboxylic acid down here. This is kind of a preview. Okay, the acid chloride can make any of these compounds. You can take the acid chloride and synthesize the anhydride from the acid chloride. So acid chloride plus whatever this nucleophile is, you can make that. Acid chloride to make the ester. Acid chloride to make the amide. Acid chloride to make the carboxylic acid. Okay, since it's the most reactive, it can make everything. The anhydride can make the ester, the amide, and the carboxylic acid. It cannot make the acid chloride. Okay, so whatever is underneath it, it can make. Whatever's above it, it cannot make. So the ester can make the amide or the carboxylic acid. And basically the amide can make the carboxylic acid. Notice everything can make the carboxylic acid. Also, what's special about the carboxylic acid is the carboxylic acid can make everything. So the carboxylic acid is special. That can make all these, or you can make it from all the other ones. The acid chloride, you can make everything, but you can only make it from the carboxylic acid. I know this chart looks a little weird. I believe they have a really good chart in your book. I don't remember what page it's on, but there's a really good chart that kind of summarizes all of this. Okay, so what we're going to do for the remainder of the chapter is just go over every of the functional groups and look at the reactions of how to make those groups.